So one of the most difficult things, come on guys, one of the most difficult things about this morning is trying to figure out what I was going to say to introduce Dave and Dave. First, Dave Ward told me just say they're the Daves. And I said, that's great, but that's no fun, since I've known Dave and Dave for a while. So I tried to think of something that was going to be fun. I'm going to skip the joke till just before Randy, because I thought in honor of him doing jokes, I should provide a story or a joke for the next one. But I thought the best sort of thing is to tell you how intelligent these guys are by giving you a personal story. I'm trying to teach my daughter to drive. Any of you who have reached that stage have the white knuckle moment, you know? I think we're going to survive this next 10 minutes because I'm sitting next to it. In Michigan, they have the torture, and in Minnesota, they have the torture of the parent. You have to drive with your child 100 hours before they can get their license. So you have to sit there in the car determining if you can live for 100 hours. You know, and I thought, okay, I'm going to make it, and I'm calmer than my husband, and I've just gotten so that I can glue the fingers after you get done with the child. You just get your hand a little untense later. But Dave Ward has twins, and I thought, twins, Minnesota, 200 hours. Oh my God, what would you ever do? Dave is highly intelligent. He bought someone. You can rent an adult. He rented an adult to take care of the twins. I've heard Dave Katz also did some exciting things with his daughter, but I don't know if I have permission to share those stories about his daughter. So I just want you to know, watch the grandparents. So I just want you to know that these guys not only know how to do routing, and I think this next presentation is really exciting because it does take the lightweight approach to backplane deadness, and I really think you ought to take a clear look at this, because more is not always better, but they also know how to make sure that they don't die of child, I don't know, child watching the driving situation. Anyway, both of those.
Thanks, Sue. Hopefully we can white knuckle our way through the next presentation. So, as you can see, we have reached a new era of cooperation and détente between two router vendors. So the Daves have spent many fine lunches, sitting in many hours in pools and taking many airplane rides, and we managed to come up with BFD. And this is a picture of your brain on BFD. We took it from Dave's plane a couple days ago on the way up here from Salt Lake, and as you can see, Utah has some really cool geologic formations. So that's why we tossed that up. And we knew that Fred was going to put her slides up, so we couldn't be shown up on that. So, BFD. What were we trying to do? Well, basically, we're running into a problem with routing protocols and building routers where we can't easily or quickly detect that forwarding planes have gone down. We're not just talking about links here or ports or necessarily certain L2 situations, but what we need to understand for a variety of scenarios, almost all of them, is when the router's forwarding plane goes down. So as a corollary to this, of course, we can't begin converging a single routing protocol or any aspect of the system until we've detected this failure. So we were focused in on solving how can we detect a forwarding plane failure very, very quickly. Obviously, in all cases, we can't use media layer alarms. Some cases in POS we can, some cases in RPR or Ethernet, etc. we can't. And also, a lot of us have been working for quite a long time and making presentations on graceful restart mechanisms, but the fundamental assumption of graceful restart is that there's nonstop forwarding. But unfortunately, until perhaps this technology, there was no way to actually detect whether or not that assumption was correct, and you just had to kind of believe it and go. So what people have been doing, obviously, for a very, very long time is using the hello mechanisms available in current routing and signaling protocols, but as we all know from the defaults, or even what you can tweak them to, they're really too slow for the type of convergence we want right now. The hello packets are really complete, the semantics of them are completely overloaded with what they actually mean. Of course, they're testing everything from the init state of the protocol all the way down to every internal piece of the router itself, control plane, back plane, potentially the in-band the line card itself, maybe the line card CPU, maybe the physical line adapter, whatever the case might be. And so by overloading those hello packets, you actually are testing different things, as well as if you begin to try and use hello mechanisms and tweak them in one protocol, you then begin to have to tweak them in all of them. So you begin kind of chasing the dog around by its tail, trying to clean up all of your routing and signaling protocols instead of solving this in one place. And of course, those in which already have tweaked fast hellos aren't always in use in all scenarios. So what can we do to solve this problem? Well, there's a couple of other proposed solutions that have been going on out there by really, really smart folks, but they're kind of, maybe they weren't at least along the lines of what Dave and I were thinking. So we can take a look at, as I mentioned, the tweaked fast hellos available in, say, RSVP, ISIS, and OSPF. And when you take a look at the implementations, or you take a look at the effect on your router itself, the cost of running these protocols with fast hellos is very, very high in the CPU, as well as the corollary impacts to the rest of the system when you begin to take up those CPU cycles, as well as they take up a lot of bandwidth on the backplane. So also, because of this, you can get a very high level of false alarms. And these also cause potentially worse things than others when you start getting false alarms from these particular protocols, and what happens to your network and the oscillation of traffic as the sending of a lot of these hello packets across your backplane may just you may starve out, depending on the architecture of the system, starve out the ability to send these hellos at this rate, thus causing an adjacency to drop. Then the hellos get through, then the adjacency comes back up, and you sit there oscillating your traffic back and forth, and your adjacencies are bouncing, and this is generally bad. One of the next issues associated with these tweaked fast hellos for these protocols is that the detection time really can't be cranked down very, very low. And what we've been hearing, what Dave and I have been hearing from a lot of folks, is that we need to get down to hundreds or tens of milliseconds of detection time for straight IP as well as MPLS or other L2 media. So we need to really start getting faster detection times of true failure scenarios. And jumping down to the last sub-bullet, basically not all of these protocols can handle unidirectional link failure. And so we wanted to try and solve that problem as well as this is cropped up. Another solution which came out, I would say, I guess maybe 6-9 months ago from a good friend, Caridi Campello, was the protocol liveness protocol, which is really what I consider the aggregated hello protocol. What it did is it took all of the hellos from all the protocols, roughly as is, added a few more TLVs, but roughly as is, and put these in an outboard engine. And then there was this outboard engine that ran the hello protocols as we know them for RSVP, ISIS, OSPF, BGP, FUBAR, you name it. And then began to tweak that a little bit more by having some TLVs which also represented other interesting things, including the initialization state of the actual protocol executable and things like this. Well, if we went down this path, and after Dave and I spent many hours talking with Caridi and other folks, was that, of course, this would cause everyone to have, all the vendors to have to re-implement their protocols, everybody to potentially have to redeploy a new protocol in which the bread and butter of the network, the routing protocols, were dependent, and this got us a little bit scary. Plus, some of the extra information in PLP wasn't along the lines of maybe what we thought that was completely necessary to solve the problem. Another solution is MARP, which was presented at the IETF, maybe a couple IETFs ago now, I can't remember. And what's interesting about this protocol, as it was presented right after Caridi's with PLP, it's still really under specification right now, and it's really trying to solve a different problem in a different environment, but I think it's going to be really interesting to follow to see what comes out as MARP is trying to be event-driven versus what we're about to present in our technology. So what exactly is the bidirectional forwarding detector? It's effectively the low overhead, short duration detection of failures between two forwarding engines. And what we mean by forwarding engines is that it does cover more than just the link or the port or the interface, but actually we're trying to cover the forwarding plane. Also, we wanted to make this protocol and this application extremely lightweight such that it could be run on distributed routers down in the forwarding plane or on the line card for sure. So we're going to decouple the fate of this protocol in the forwarding plane from what's going on in the RP, so now we can more easily implement graceful restart in distributed routers, and of course decouple it from what's happening on the RP during failover, whatever the case might be happening. Also, we wanted basically to take some of the lessons of the past, which both Dave and I learned the extreme hard way, and actually from the get-go have this protocol work on any data protocol being forwarded between two systems, v4, v6, 802, whatever the case might be. And so, as you'll see in a little bit, it basically runs on top of anything. It's rather generic. The next thing that we argued over was whether or not we could optimize how to send BFD beyond just having point-to-point relationships between two adjacent routers. And can we possibly use multicast? And actually we followed our old adage that if multicast doesn't solve the specific problem that you're trying to solve, don't go down that path. And in this particular case, it didn't solve the specific problem that we were trying to hit. So also, the next thing we wanted to make sure was that we could have disparate systems of disparate capabilities sitting next to each other. We could have, the biggest, baddest routers out there in the net sitting next to Kathy's cable modems, whatever the case is, if she was actually peering to them, through them, or whatever the case, and actually be able to handle this by having point-to-point relationships and negotiating the parameters between the two adjacent routers. So those were the goals, and let me go through a quick overview and then we'll take a look a little bit more. We're not going to go into too much depth here on exactly what the packet format is, but an overview of what we're looking at. So we're looking at trying to detect failures between next hops in the data plane. BFD is a fixed field protocol. It's really, really lightweight, we think. And basically, we can pass this over any encapsulation that's appropriate, and we have a couple of different modes that we're going to talk about. So what we have is a separate session for each communication in the data path between the two systems. And you set this up between all of the adjacent routers. Each one is talking to the other. There is no, at this point, there is no ability to, again, multicast between an array of systems or a bunch of systems. So also, we can handle unidirectional links, although it's implementation dependent on how this is going to happen, but it was critical that we were able to handle unidirectional LSPs. And of course, what we learned, as I mentioned before, is that slow systems have to be able to play with fast systems. So what you're going to see in the protocol is that each router is going to send how quickly they would really like to detect a problem and how fast they're willing to detect receive BFD packets from the other router, so that way both directions are negotiated and you go to the weaker router. So what does it really look like? So the packet is really simple. Version, of course, we've got an I hear you bit, because as you're going to see, we're sending two independent streams between routers, and to get the bidirectionality, we've got an I hear you bit, so if you suddenly don't hear your neighbor, you can let them know as quickly as possible. We got some diagnostic code so we can actually debug this thing. A detection multiplier, so that way we can have a nice little multiplier as is in other protocols to be able to have your detection time set by you. We've got a couple of discriminators. In other words, the forwarding plane, my discriminator is the forwarding plane on the local router. Your discriminator is the one that you think you're talking to on the remote router. You negotiate so that way you're both talking about the same thing, and voila, the communication is sane. And then, as I mentioned, we're going to negotiate how fast we want to transmit and how fast we would like to receive packets from the other end. What's interesting about this protocol versus what we learned from the IGPs and other protocols is that we want to be able to change all of these values on the fly without actually tearing down the session and going back to, say, a init state 0 or something like that, which is what we're used to with, say, OSPF. Anytime you change one of the values, you're tearing down the adjacency, you're moving your traffic around. After making this mistake, for how many years have we made it, Dave? We hopefully think that we're going to try and get over this and continue. So as I mentioned, it's fixed field. So what does this really mean? This means that once you've negotiated these values, you already know what to expect to receive from the other end. So from the vendor side, this implementation becomes much easier. And the same side, once you know what you're supposed to be sending to the other side, again, this hopefully becomes very, very lightweight, and we can shove this down in the forwarding plane. So because it's lightweight and we can do kind of some predictive type mechanisms, we think we can achieve tens of milliseconds of detection time for IP networks. And the only time that we really need to pay attention to this protocol, as it's just sitting there firing away in the background, is when anything changes. And either we're going to check the I hear you bit and whether or not they stopped hearing us, whether or not they send a value such that they're saying their session has gone away or their forwarding plane is hosed, or they want to adaptively change one of the values of the parameters. Anything you want to add at this point, Dave? You're my straight man.
I have a microphone either. Oh, yeah. I'll just interrupt you and throw things if there's anything I disagree with. So.
Okay.
The discriminator stuff, we talked a little bit about unidirectional links, and you can imagine having a whole bunch of links going in one direction and everything coming back through a routed path in the other direction. And so one of the functions of the discriminators is so that you can separate out the return packets and know which sessions they apply to.
So what are the issues that we're facing right now? Dave and I are working to figure out how fast we can actually make this go. So we built the protocol with millisecond timers. We got burnt over the decades with intervals that were too large, such that you can't get below a second, and that's really not acceptable, of course, if you want to get down to millisecond detection.
Actually, the fields are specified in microseconds.
Oh, sorry.
So we can do really bad things.
Should we do that to nanoseconds, or?
Well, the dynamic 32 bits is nice because it gives you 1 microsecond to an hour and a half or something, which is probably a reasonable dynamic range.
Cool. I'll change my slides. The detection multipliers to handle any packet loss or delay going across the links or in the remote forwarding plane, any queuing, etc. So that's what we've got there. And then the security issues we have, we're recommending that we again use the VJ Dave Meyer TTL hack, where we can set a well-known value and then begin to chuck packets that aren't matching that TTL. Or of course, it's highly recommended as you run, if you're going to use, say, a router ID or something like that, you don't make this a routable address outside the domain, and there you have security by obscurity, and they can't even reach that particular address on the net.
And if you're really paranoid, you can run it over an IPsec tunnel since it runs over anything, but your detection times might not be as good.
So, again, from the comments that we received from other folks, basically everybody refers to BSD as the link deadness detector, and it's really not. And it's really not just link deadness, because not only are we passing it through the forwarding plane, but both ends have the ability to trigger the loss or the failure of a forwarding plane due to any reason. In other words, you can send a failure notification that you stopped hearing the other side, or you can send a note to your adjacency that your forwarding plane has croaked. Did you want to interrupt me, Dave?
Apparently not. Yeah, I have a question. In the context of BTSH, a lot of people have asked me if we could generalize that mechanism to cover a bunch of other protocols, and I'm wondering if there's anything in the work that you guys are doing that would prevent us from doing that and applying these mechanisms to those other protocols.
Yeah, absolutely nothing. We can generalize BTSH extremely easily, and we'll fit right into that model.
Okay, thanks.
It's all things to all people.
Okay.
So, I don't know exactly what Dave's doing in his code, but I think most of us are actually generalizing the implementation that we can quickly and rapidly allow any protocol to use the TTL value as a discriminator. So what I was mentioning before was that as the local router can actually trigger a diagnostic code that represents a failure of the local forwarding plane, and really kind of what are we talking about here in some of the scenarios? Well, I've got a few listed out here. The line card has become disconnected with the RP. Who knows why it's gone out to lunch? There's an inability to update the fib, or the fib is hosed, some kind of error during download that the local router detects. Protocols crash, don't reinitialize for some particular reason, or basically any number of internal failures that we're seeing can trigger that cause a forwarding plane failure. And because of the decoupled nature of the protocol, we can send that notification to the remote end to basically shun traffic from yourself and keep network traffic going through another link or forwarding plane that is available. So again, of course, the I hear you field is that you stopped hearing the protocol packets from the other end, and that means that you can suddenly trigger by sending a false to say, hey, I stopped hearing you, so that means the 2U path is hosed at that particular point if it's missed.
Yeah, this also is what makes the three-way handshake on both session up and session down.
So here's about as good as it gets, is my ability to do PowerPoint diagrams, but I can manage to get colored arrows and boxes up on my slides. And the async mode is basically when you use the control packets and you have independent streams running between the two routers. Again, you're negotiating the RX and TX values such that A, B, and C can all be of different capabilities, but the protocol will work representing the forwarding plane for which the packets are traversing.
To note, these three routers could actually be on a single medium, or they could be point to point.
There's a second mode called echo mode, in which their control packets run at a fairly sedate rate from which you've negotiated the RX and TX values. And then there's another form of the packet that is basically sent, sourced and destined to yourself through the forwarding plane of the remote router directly in the path as regular packets. So you're going through and actually testing the true forwarding plane back to yourself. And the sender is also, of course, the receiver of these packets and is in complete control of how fast it can then detect locally the failure of the remote end. And this is for extremely aggressive detection times. So there's two independent streams in the async mode, and then they're sending packets directly through the forwarding plane of the remote router back to yourself in the echo mode.
It can also be argued that the echo mode better tests what you're trying to test, since you are actually forwarding through the remote system. Although it's, depending on hardware architecture, it may be, hitting a line card and bouncing back out again. But at least you sort of have a basic liveness of, is that box actually able to forward packets?
But what you can see from the multicolored spaghetti is that you have twice as many packets on the wire, or at least twice as many packets on the wire at any one time, because you have to have independent echo streams between the routers.
Andrew Partan. With the echo mode, do you have the capability of adding essentially opaque data, so I can send, all ones, all zeros?
Yeah,
patterns?
the format of the echo packet is outside the scope of the specification, which is a phrase you will see numerous times. One of my goals is to make a minimalist specification that is fully interoperable, and those things which are not necessary for interoperability are, in some cases, their hints are, here are some things you might want to do, and in other cases it just says party on. So the only thing that's specified about the echo packets is a UDP port number, so that you can sort of know what they are for, from outside the protocol, but the payload of said packets is entirely up to you.
Yeah, the length and payload is completely open, and you can send whatever you do or don't want. So, as Dave mentioned, we handle unidirectional links because the packets can be demuxed independently of the interface from which they've been received. And via the discriminator field, we can determine what forwarding planes we're talking about on the local and remote end. And how this is implemented is basically up to anybody implementing it. But the key thing there is that when you're talking about unidirectional LSPs, the packet coming back or the other stream can be coming in from anywhere, and the protocol can figure out what the heck it's talking about. So also, we wanted to do this over 802, and taking a look at the topology, basically it's routers talking to switches. And we wanted to be able to cover this particular case because going from that ultra generic topology, it's really what we're trying to do here is solve the subnet reachability problem that we have on Ethernet. And generally, as you can read in the bullet points here, basically one of those uplinks croaks and goes unidirectional. In all cases, the link doesn't immediately go to downstate in a timely fashion. And so what this means is that, of course, looking back at the picture, if one of the router links doesn't actually detect the failure and goes unidirectional, you're going to be blackholing traffic, and we've been seeing this for years on Ethernet segments between routers connected via switches, or if they're going directly to something like a data farm below, that traffic isn't making it.
And in fact, it may be even worse, because oftentimes in that topology, the routers are not talking to one another on the subnet that has the data farm on it. So one of those links from the router to the switch fails, and both routers continue to announce the subnet as being reachable, and this will persist indefinitely until the phone starts to ring. So we have a number of customers going, please, 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 please fix this problem.
But note, over 802, echo mode between switches really doesn't work. Switches don't work. The Ethernet switches don't work this way, where you can basically just switch back to the MAC address from which it was sent. So this is the case, as you can see in the generic topology, that we're using async mode between these switches. So what does independent streams really buy us? Well, what this allows us to do is have independent streams per address family, so we can detect when specific address families go down versus others, and don't necessarily have to take down all forwarding planes on a card, including, of course, the multi-verf issue. And you can have independent streams per verf as well, so you can actually get to the point where you can figure out what verfs are up versus what verfs may be having issues for one particular reason or another. And of course, the independent echoes as well as async mode works just fine for different address family or different verf failure detection. So I think we might be, I'm just about done. I've only got a couple slides left. So basically, in conclusion, we think the protocol's really simple. It's not trying to be the aggregated hello for all other protocols moved into a new protocol. Instead, we leave our routing protocols just the way they are, running in the fashion and manner and configuration which we've all grown to know and love, and instead we can tweak the heck out of this really simple protocol that's running really, really fast. Because it's fairly simple and because it's a fixed field, we think it might be fairly easy to implement, and it's decoupled. We can handle both bidirectional and unidirectional failures. We can have adaptive changes to any of the values in the packets itself, so that way we're not tearing down sessions and necessarily having false notifications just because the values changed, as I mentioned. We can do this without upgrading software in the switches between the routers. And one last thing I wanted to note was that the protocol liveness protocol, as I mentioned from Caridi, this BFD with Caridi's agreement is going to replace that idea, and that idea is just going to stay in the books for history. So basically, from the negotiations that Dave and I made at his pool, we got this picture, and really BFD is detecting when the forwarding plane has gone belly up. Go ahead, Sue.
Am I live? Okay. One question is, some people are looking for millisecond turnover for some of the modems for voice over IP. If you go to millisecond and they're looking at 20 milliseconds, how are you going to go below that for the aliveness detection piece?
It's an implementation issue.
So
there's nothing in the protocol to preclude arbitrarily fast detection. It really boils down to, from a practicality standpoint, what can you do in software? What can you do in distributed software? What can you do with a little bit of hardware assist?
Right.
And I suspect the answer to how fast is going to be, improve an order of magnitude, with each architectural. We're not going to get 5 millisecond detection times in the first release, but if we could get Mac chip manufacturers to bury this in the silicon, that would be really nice.
Yeah, I was just commenting on your earlier place when you said millisecond and the size of field. You might want to think about.
Oh, the field is in microseconds.
Yeah.
Yeah.
Yeah. So, how does this relate to the forces work? I mean, this is the moderator moment.
To which work?
The forces work, which is talking about downloading things from a central processor into forwarding plane processors.
Shift left. So basically, this could be part of the forces work, depending on the control plane or how the implementation is done inside the router. The protocol can be plugged, as I mentioned, through the different scenarios into different failures that Forces deems important or different things that they want to specify. Basically, how it fits together is, I think Dave kind of summed it up, that because the hooks are there to hook it into everything, it's everything to everybody.
So you're seeing it as a heartbeat protocol for the Forces download negotiations?
Think of it as this little box on the side, which occasionally something pops out at the top that says, I can't reach this neighbor's forwarding plane anymore. Oh, I can reach this neighbor's forwarding plane now, and then it's an implementation issue after that.
To take care of the actual
Do whatever,
notifications.
do whatever you want to do within your system.
Okay.
Randy Bush, IIJ. I'm just a dumb operator, and what's this going to mean to me? Are you saying that you're going to start slipping this stuff under, for instance, ISIS or whatever that other IGP
that other,
was.
the other protocol, yeah.
Yeah, or BGP, and so I'm going to see different convergence characteristics. Am I going to see, this is everything to everybody and has all this wonderful tuning stuff, am I going to see interesting things that I'm going to have to work out within my network or with my neighbors as far as tuning, timing? What's it going to be like driving this thing, and where does it show up in my car?
Where does it show up in the config? One can imagine a scenario with, perhaps in your ISIS or OSPF interfaces section. Oh yeah, that other thing that we suppressed. This little extra line popping up down there that says, "I would like to leverage BFD notifications, please," and perhaps. You might have and I'd like to try to reach a detection time of.
And I really want to do that because.
Well, I could just make it happen automatically, but.
No, but
right.
Why do I really want to do that?
Why would you want to do this? Okay, well, I mean, the easy scenario is people with Ethernets in their POPs, who have n-second detection times when the plug falls out or the switch powers down, or the neighboring router goes down because you don't have any signaling other than the protocol IGP hellos. That's probably the first order helper for most people. And as far as tuning goes, I've converted from knobs are great to there are of 100 ways to set configurations. Only one of them will actually work. It's part of the creative implementation side of this, but there's nothing to preclude having no knobs and having this just work.
I run multiple vendors.
Well, if one of them does a particularly good job of working with no knobs, it will force the other one to play along because of the way the protocol works.
So in addition, I agree with Dave that Ethernet is kind of the primary motivation for most operators, but the other one is that as I went through the scenarios of potential internal failure conditions to a router, the router actually can now tell the other side that it went brain dead for some definition of brain dead. And in the past, all we had the ability to do was wait for either the IGP hellos or wait for the thing to be just hosed and sit there until the phone rang. And then somebody had to do something about it. So hopefully we can solve those two, or come close to solving those two meta problems.
Thanks.
There's also liveness on GRE tunnels and LSPs and things that are kind of missing right now, but go ahead.
Avi Friedman. I think it's a very interesting area of work. I think as an operator, I think it's interesting. But one of the things that keeps some people awake at night is actually not just whether or not the route processor, the main CPU of one router can talk to another, but whether the forwarding information has actually been propagated properly across all the line cards in the router. And this doesn't, applies to some vendors and not others, and I don't mean to, pick particularly, but just it's true that in general, 6 years ago, the router would be up or rebooting, and now there are a lot of different ways in which multiple vendors' devices can become sort of confused. And I think that extension of this, if it works well in the way you're describing, to look at how you could perhaps detect inconsistencies in line cards that are hard to find because sometimes it depends on the source interface and the dest interface, the testing takes. I think that would be an interesting area.
It's an interesting problem. Yeah. I think it's one with an infinite number of causes. I mean, this is sort of like, how do you write software that detects all software bugs?
Well, but one of the fundamental problems, as you identify, of the graceful failover is, when are you dead enough? When are you confused enough that you actually want to do the switch?
Right.
And Akamai, one of the things we run is the world's largest inconsistent forwarding plane detector, because we talk to the provider and we say, you can't get somewhere, and they say, look, I can. I ping from the router. They say, well, you probably need to come from the right source interface to verify this. And they go, oh, look at that. We do need to reboot the device. We just didn't know.
Well, one could certainly use BFD as the as the hated messenger. the problem of, how do I tell whether my forwarding tables, my N forwarding tables are all consistent is certainly outside
Right, I don't
the
want to
scope
pick
of
on
this
that.
protocol.
I don't want to pick on that in particular.
Right.
And
But
you
but
needn't-
for example, if you have little gnomes running around in your router comparing tables,
Yeah.
and you find that they don't compare, and you're not sure what to do, then you can kick BFD and say, please tell the other guy to not talk to me for a while.
Yeah.
And those hooks are there in the protocol.
Okay, thanks.
I guess the Daves are done. Thank you. No? Yes.